Hello and welcome to this AQA oxidation reduction and redox reactions revision video. Nearly forgot it there. My name is Chris Harris and I'm from AlleryTutors.com, and the whole point of this video is basically just to give you a very quick overview into this part of the AQA syllabus, and as you might imagine, obviously it's very specific to AQA from this particular one. So the PowerPoints that I'm going to use here, you can actually purchase them as well if you want to use them for whatever you want to do with them. If you click on the link in the description box just below this video, you can go and get them from there. They might be pretty useful because you can write them, print them out, write them, whatever you want to do, and use them for your revision notes. Yeah, like I say, these are very targeted towards the AQA specification, this one in particular, and so obviously it's tailored to the specification, and so they're the points there. Okay, so let's make a start. So we'll look at reduction and oxidation. Now we need to know a few things about this. So basically, reduction and oxidation we need to know in terms of electrons. So electrons are transferred when reduction and oxidation occurs. Okay, so we can use the acronym OILRIG to help understand what is happening. Okay, so oxidation is the loss of electrons, that's the oil bit, and reduction is gain, that's the rig bit. So you need to know reduction and oxidation in terms of them. You need to be looking out for things like that as well. So if we have a look at this reaction is when calcium is completely burnt in oxygen. It involves the reduction and oxidation of the elements involved, and we call this one a redox reaction. So let's find out and see why we call it a redox reaction. Look at calcium. Calcium is being oxidized because it's losing electrons. Look, calcium is going to Ca2+. So there's the Ca2+ there because this is calcium combined with oxygen, so it's Ca2+. And if it's going to form Ca2+, it must be giving up 2 electrons as well because we're forming a 2+ charge. So also, when you're writing your equation, make sure it's balanced. Look, it's neutral on this side, and it's also neutral on that side. See, 2+ and 2 negatives. Okay, so let's look at the other half of it. So in this reaction, oxygen is being reduced as it's gaining electrons. So you can see here, half O2 in the full equation. This is half O2. It's gaining 2 electrons, and we're forming O2 minus. And this is obviously going to react with the Ca2+ to form CaO. So you can see the electrons are being accepted. So this is an example of reduction. This is reduced. It's the oxygen that's been reduced here. So really, really, really important, this bit, and I think some people get a little bit confused with this bit. It's a little bit confusing, I suppose. Reducing agents. This is different from reduction. Okay, so reduction is a process. Reducing agent is an actual chemical that we're looking at. So reducing agents, these lose electrons and are oxidized themselves. Okay, so reducing agents, unlike reduction is the gain, reducing agents actually lose electrons. So they're oxidized themselves. So calcium is losing electrons in this reaction. So in this case, in this reaction, calcium is the reducing agent. Okay, it's really important you remember that. And the oxidizing agents, what they do is they gain electrons and are themselves reduced. So oxidizing agents gain electrons. There is a difference between a reducing agent and reduction. Please make sure you know the difference in oxidation and oxidizing agents. Make sure you know the difference. Oxygen in this case is accepting electrons, so oxidation is the oxidizing agent. All right, okay. Now, the most important bit of this topic really is the oxidation numbers, and there's a set of rules that you have to know, and there's a few exceptions that you need to be aware of, and you've just got to remember these. Some of them you can work out actually, but some of them you've just, well, actually all of them you can work out, but some of them you've got to just try and remember. So basically each element can be assigned an oxidation number, or sometimes it's also known as an oxidation state. So this number depends on a set of rules that we're going to look at here. So the first one, uncombined elements, so are always 0. So things like Cl2, FeO2, they're always 0. Okay, so that makes it a bit straightforward. Ions, the oxidation number is the same as the charge on the ion. So for example, Cl- is going to have an oxidation number of -1. Ca2+ is going to have an oxidation state of +2. Okay, so that's pretty straightforward. Group 1s are always +1. So for example, potassium in potassium chloride, that's +1. Group 2s are always +2. For example, calcium in calcium oxide, so that's always +2. Aluminium is always +3. In this case, aluminium oxide is always +3. So there's no exceptions to that one. Hydrogen, right, here's where the first exception comes in. Hydrogen is always +1. Okay, so here, for example, in HF, hydrogen is +1, except in hydrides where it's -1. So here's sodium hydride. Hydrides are just where hydrogen is bonded to a metal, like sodium, for example, like group 1. It could be group 2, 1, to be honest. They're called hydrides, and hydrogen is -1 in this case. Chlorine is -1, okay, except when it's bonded with fluorine and oxygen, okay, and it would have a positive value. So, for example, it would be -1 in KCl, so chlorine's -1, but chlorine has a value of +3 in ClF3, okay, so F would hold the value of -1, and you've got 3 of them, so that's -3, so chlorine must be +3 to make sure the whole thing balances, okay, so really, really important. Make sure you kind of watch out for that, because you'll see that quite a bit. Fluorine is always -1. That makes it pretty easy. It's nice to see. So basically, the most electronegative element takes priority. So fluorine is the most electronegative element. So it always has this priority oxidation number of -1. So for example, KF. And finally, oxygen is -2, except in peroxides where it's -1. And it's +2 in OF2 because fluorine takes the priority in this case. So for example, it's -2 in lithium oxide, so Li2O, so it's -2. But oxygen has a value of -1 in hydrogen peroxide, that's H2O2. Basically, per oxide means for every oxygen. So you can see here, we've got a hydrogen for every oxygen. 2 hydrogens, 2 oxygens, hydrogen peroxide. So it's pretty smart. Okay, right, so let's look at the next bits. Right, so we're going to work out some oxidation states. So I'm going to go through a few examples here and kind of give a little bit of an explanation. I've dragged the table along onto this side so you can obviously use them. So we're going to work out the oxidation states of the elements in red. So let's look at this one. Nitrogen. Hydrogen has got a charge of +1. Remember, it's there. Look, it's not a hydride, that, so it's always +1. You've got 3 of them, so that means nitrogen must be -3. Okay, this is rule number 6. Okay, next one, H2S. Hydrogen, again, is +1, which is there. Sulfur is bonded to these 2 hydrogens. So sulfur must be -2 because the overall charge is 0. So there you go, it's -2. Again, it's rule 6 again. It's always coming up. Okay, O2. Okay, O2. So oxygen, remember this is an element, uncombined elements, that's them there. Always have a value of 0, so that's rule 1. There it is. Okay, 0. Dead easy, that one. Okay, next one, H2O2. This is your exception. This is hydrogen peroxide. Look, here it is. Where is it? There it is. Okay, this is rule 9, this one. Oxygen is -2, however, except -1 in peroxide. This is a peroxide, so oxygen is -1 in this case, not -2. So, and also, obviously, we've got rule 6 again because of the hydrogens. So, it's -1. Okay. Remember, when we're stating oxidation numbers, we always state for the single element, not for both of them. So, it's not -2. In this case, it's -1 because we're looking for the oxidation state of one oxygen. Okay, H2SO4. Right, a little bit more complicated here. We've got a few more things to work out. Just find the most electronegative. That's probably the best place to start. Oxygen. That takes priority. Oxygen is -2. Okay, got 4 of them, so that's -8. The hydrogen is +1 individually. There you go. So therefore, it's going to be +2. So if that's -8 and +2, this must be +6, okay? Because it makes the whole thing balance, the whole molecule is neutral, okay? Right, this one's a little bit different. SO4, 2-. Notice this one's got a charge. Not too difficult, to be honest. Work it out the same way. Oxygen is -2, okay, individually. You've got 4 of them, so that's -8. Sulfur, basically, you've got to add the numbers up until you get to that charge. So this is -8. Sulfur's got to be +6. Because -8 plus 6 gives us -2. So that one, like we say, all the oxidation state must add to the overall charge of the molecule. So this one is obviously going to be +6 in total. Take note of that charge, it's very important. Okay, right, let's work out some more oxidation numbers. Now, Well, again, we're going to work out the ones in red, but you've got to watch out for transition metals because these are variable oxidation states. So let's have a look at this one, Fe2O3. This is following rule 9. So rule 9 is basically the value of oxygen. It's -2. We've got 3 lots of them there, so that's 3 lots of -2, which is going to give us -6. That means that both ions are going to be +6. That's what we've got there. We're going to divide that by 2 because we need to know what one ion is, and that's +3. Okay, so this is iron oxide. But look at this one. Okay, this one's iron 3. And we use the Roman numerals to kind of put 3 on there to show that it's +3 states. So it's iron 3 oxide. But this one is iron oxide 2. Okay, but look at the formula. It's different. Oxygen's -2, so iron has got to be +2 because the whole thing balances out. This one is called iron 2 oxide. Okay, so we've got iron, Roman numerals 2, oxide. So we know that the iron is +2 charge. Iron here is 3. Okay, so just to make sure this all balances out. Notice, make a note of that, make sure you know that. But look, it's got a variable oxidation state. Same element, different oxidation state. Very typical of transition metals. Okay, here's another one. Vanadium oxide. Okay, so this one, again, oxygen is -2. Vanadium must be, to turn this into 2+, must be +4. So we call this vanadium 4 oxide. Okay, remember it's got to add up to this charge here. Look at another one. Here's another vanadium compound. Vanadium oxygen -2. 2 of them is -4. Total charge is positive, so the vanadium must be +5 to make sure that you get this positive charge here. So this is called vanadium 5 oxide. Vanadium's a transition metal. You can see it's got 2 different oxidation states. So very typical of transition metals. Look at the Roman numerals. That tells you what the oxidation state is of it. Okay, oxidation or reduction. Now this is where we can use these numbers here. So reduction is a decrease in oxidation number, and an oxidation is an increase in oxidation number. So let's have a look at this reaction. This is 2Na plus Cl2 will form 2NaCl. So if we look here, oxidation states of sodium is 0, chlorine 0 because they're elements. Sodium in here is +1, chlorine is -1. So what we're going to do is we're going to assign, basically we're going to decide if it's oxidation or reduction. Here it's oxidation, sodium's being increased, there you go, it's gone from 0 to +1, so this is sodium being oxidized, increase in oxidation number. And guess what? Chlorine is being reduced because it's going from 0 to -1. There is a reduction in oxidation number. So that's all you're looking for really. Write down your oxidation states. Has it gone up? If it has, it's oxidation. Has it gone down? That's reduction. Dead easy. Okay. So sodium, looking at the reducing agents, remember, really important. Sodium is a reducing agent. Itself has been oxidized. Okay, so that's the reducing agent. Chlorine is the oxidizing agent. Itself is being reduced. Okay, so make sure you know this. This is going to come up quite a few times. Okay, right. So we've looked at some half equations right at the start of this video. We looked at some half equations, okay, and we need to know how to balance these, okay. So half equations basically show us reduction and oxidation stages in 2 equations, okay. So all half equations must have electrons in. That's a classic sign of a half equation. It has to have electrons in. So there's a set of rules that we can use to work this out. So basically what we do is the first thing, we write down the species before and after the reaction. So when we look at the example, we'll show you that. Then what we do is you balance any atoms apart from oxygen, hydrogen. We'll deal with them later. Okay. Then what we do is we balance any oxygens with water. We balance any hydrogens with H+ ions. And then finally we balance any charges with electrons. Okay, so let's apply this to an example. So, this is quite important actually, I suppose. These ones with the asterisks, you might not need to do these if there's no oxygens or hydrogens, so you just need to watch out for them. Okay, so let's look at this example. So we're going to write a half equation showing the conversion of Fe2+ to Fe3+. Okay, so let's write down the species before and after. So we're going from Fe2+ to Fe3+. Balance any atoms apart from oxygen and hydrogen. Well, look, they're already balanced, so that's fine. Then we balance any oxygens with H2O. We haven't got any oxygens, so we can skip that step. Balance any hydrogens with H+ ions. Again, we don't have any hydrogens, so we can skip that step. And then all we have to do is balance any charges with electrons. Now if you look here, that's a 2+, that's a 3+, Electrons are negative, so if I put a negative on this side, that'll bring this side down to 2 plus, and that'll balance it with the one on the left. So there it is. So total charge on this is +2, total charge there is +2, so that's it balanced. Okay, let's look at the other half of this equation. Okay, oh, that's quite important. This is oxidation. Okay, so this is showing obviously an increase in oxidation number. So we're going from 2 plus to 3 plus. So because that's an increase in oxidation number, that's oxidation. Okay, so let's look at an oxidizing agent. So this is oxidation. So we need an oxidizing agent to allow this reaction to happen. So this is only one half of the story. So again, we're going to use as our oxidizing agent, we're going to use MnO4- going to Mn2+. Okay, so again, let's write down the reaction species before and after. MnO4- to Mn2+. Okay, balance any atoms apart from oxygen and hydrogen. Well, the only ones that are apart from oxygen and hydrogen is manganate. They're balanced already. We've got one there and one there. So that's fine. It's already balanced. Balance any oxygens with water. Okay, so you see we've got 4 oxygens here. We haven't got any on this side. So to get 4 oxygens on that side, I need to add 4 waters on the right. We can only balance oxygens with water. Okay, we can't just use oxygen. So we balance it using water. So we have 4 H2O. So now we've got 4 oxygens on this side and we've got 4 oxygens on that side. Balance any hydrogens with H+. So you can see here we've got 8 hydrogens on the right. So we need 8 H pluses on the left here. So there it is. There's your 8 H+. Then once we've done that, we then need to balance charges. Total charge on this left-hand side, you've got 8 pluses here and a negative. So it's +7 on the left. And on this side, it's +2. So I need to bring this +7 down to +2 because we're going to add a negative electron. So to do that, we need to add 5 electrons to the left. So if I add up the charges this side, that's going to be 8 positives there and 6 negatives. So that's going to be +2 overall on the left, and it's +2 on the right, look, because that's neutral. So that's the equation. That's already balanced. And this is showing reduction. So reduction is the, remember, reduction is the gain of electrons. So this is obviously gaining electrons. There it is, manganate. Gaining the electrons to form manganese 2, sorry. So this is basically showing a reduction process. Okay. So what we need to do, them 2 half equations, this one and the iron one, we need to combine them to form a full ionic equation. Remember, these are half equations because we've got electrons in. So an ionic equation is one without the electrons. So 2 half equations, we can combine them to form a full ionic. Make sure your electrons balance. So let's bring in these 2 equations again. Remember this one. This is the one where we had oxidation, Fe2 plus going to Fe3 plus an electron. This one showed reduction. So this is the one that was manganate, going to manganese 2 plus, or manganese 2 plus. Okay, so 2 reactions. Now what we have to do is try and combine these. Okay, but if you see on there, the electrons don't balance. You've got 5 electrons in the bottom one, and only 1 in the top. So what we have to do is multiply that top equation by 5 to make sure the electrons balance. This is if you're kind of mathematically minded, even if you're not. I mean, you would have done this at GCSE maths. This is just a simultaneous equation. All we're trying to do is yes or no simultaneous equation. Then you thought you got rid of it, but it's actually back in chemistry. So this is a simultaneous equation. We're just trying to make sure the electrons are balanced. So we multiply that top one by 5, and there's our equation there. So we rewrite out the equation. Everything is multiplied by 5. 5 Fe2 plus, 5 Fe3 plus, 5 Fe minus. So now we're going to use that equation and that equation, and we're going to combine these 2. Okay, cancel the electrons out. That's the ultimate aim. Cancel them out, and we're going to combine the 2 equations. It's literally that plus that plus that. So everything on the left-hand side of both equations we put down here. Everything on the right-hand side of both equations we put there. So that's what we should have. Okay. Very important, you should have no electrons in the final equation. If you have, you've done something wrong. Okay, you should have no electrons whatsoever. They should be cancelled out at this stage. Your full ionic equation shows both reduction and oxidation. So this was oxidation, that was reduction, this is redox. This is both. Okay, so this is an ionic equation. Really, really important. And that's it, really. Hope that was useful. This is a summary for all the redox and oxidation, etc. Make sure you know them exceptions. They're pretty important. Make sure you know obviously how to balance your half equations. You know how to set them out and combine them to form ionic equations as well. But yeah, if you these PowerPoints, like I say, you can get them. You can buy them from the link that you can click. If you click on the link in the description box for the video just below, then you'll be able to get them there and do what you want with them. All right, that's it. Bye bye.